So where the last video discussed a formula, and in particular we discussed sodium carbonate, and it allowed us to look at that formula and recognize that we could then say we had two atoms of sodium in one, sorry, there's not enough space there, one molecule of sodium carbonate, or we could go through and have said 2 moles of atoms of sodium were equal to 1 mole of molecules of sodium carbonate. So that was useful because we had those now ability to convert between substances using chemical formulas. Well, a chemical formula is very similar into a chemical reaction or to chemical equation, because the chemical equation now allows us to convert one substance to another through a effectively legitimate process. If we go through and look at our formula, we're kind of arbitrarily making the connection of sodium in sodium carbonate. Might be nice if I put in that C. That isn't how it's made. How to make it would require an actual chemical equation to understand that. So what the formula gives us is this ability to convert within the formula, but it's kind of an arbitrary system because we can't actually make those things happen. The chemical equation actually allows us to make those things happen. Okay? And that's why chemical equations become useful. If we were to go through and try and provide simple instructions, so again, what we're going to do is step back from the chemistry and look at a larger thing. So if we were to provide instructions on how to build a bicycle, assuming we just had wheels and a frame, well, we could go through and say that we need those 2 wheels, and we put those 2 wheels together, okay, and this is our putting together process, we get our bicycle, and so we've assembled it. We could also simplify this because we have that repetition of wheels, and that takes up more space, so we could put a coefficient in front. 2 times wheels plus that frame gives us the bicycle. And so now we have a chemical equation to represent this process. So we could then use this chemical equation to come up with some answers. So if someone built 4 bikes, how many wheels and frames were used? Okay, you could probably come up with that calculation pretty straightforward and simply in your head. Okay, but as we've been talking about again and again and again, don't focus on, yes, I can answer this question. Focus on what was the process you used to answer that. And for those of you saying, well, I just multiplied by 4, that doesn't really work either because you're only answering this question. Okay, we again want to scaffold out to the process that we've been using. So in this question, we're asked 2 things. We're actually asked how many wheels and how many frames. So it's really 2 separate questions. So if I want to know how many wheels were used, I would have to use the given information. Okay, I'm given that I have 4 bikes, and I'm given this big equation that now shows all of those intricate pieces. So which piece of information do I want to use first? Okay, the analogies that we've been using in the past is that we probably would want to move to using the purple information first. I want to use those wheels from the purple information because those are the same unit, whereas bikes isn't the same unit as wheels. Because I'm pulling it from the purple information, I know that that is 2 wheels. Okay. Now, what do I want to relate those wheels to? I could relate them to frames. Am I spelling wheels right? Looks like it, allegedly. I could relate them to frames, but that's not useful because I'm not given frames. So instead, I'm going to relate those wheels to bikes. What is that conversion? Well, there's 1 bike. How do I know that? I looked at the chemical equation, and there's an implied coefficient of 1 in front of that. Okay. In my conversion process, that now introduced this concept of bikes that I don't want, so I would need to cancel that, which means I know bikes needs to show up in the numerator so that that unit can cancel. Am I given just bikes? Sure enough, I am 4 bikes. Okay, so the process is establishing where those units belong and how we multiply this out, and we would then say that we need 8 wheels. We would do the same thing for frames. So I'm going to say you should go through and actually write that down now. pause the video. You're not writing it down. Pause the freaking video. And ta-da, there's the answer. If I get a bit tense, sorry, I'm getting a bit stir crazy. My office at home is literally a 5x5 closet. So with that, we could go through and set up our work, and our answer comes out as 4 frames. So to build 4 bikes, I need 8 wheels and 4 frames. We might be, okay, that's simple. We understand that process. Okay, well, if you understand that, then you should be able to answer this question. So go through, set it up, pause the video again, see what you can come up with. Yeah, that means pause. That's the little click with your mouse, the 2 lines next to each other, or you can just click the picture. Just click in the middle and it'll pause the video. You didn't want to click? Try space. Just hit space, it'll pause the video. And your work should look like this. Ta-da! I'm amazing how fast I can write. So we get 3 bikes either way we look at it. Okay, so cool. Does your work look like this? If it doesn't, you should be continuing to go back, reverse the video, and try and establish what that process is again. Okay? Because again, that process becomes critical for when we make this more difficult. Okay, so let's try another one. Given just 2 wheels, how many bikes can be made? So again, set up your process and see what you come up with. You'll notice the video is still running, isn't it? That's because this is an interesting question. Okay? This is typically how a question would get phrased in chemistry, and it's actually poorly written. If you're only given 2 wheels, you can't make any bikes because you don't have a frame to which to attach those wheels. Guys, but unfortunately, chemists do phrase questions like this. Okay? And really, it's not chemists, it's chemistry instructors. What we're saying by this is given just 2 wheels, okay, and unlimited frames, how many bikes can be made? Man, that was awful. Let's try that again. And unlimited frames, how many bikes can be made? Okay. This is us being nice because in the previous questions you had to address both wheels and frames. By now saying unlimited frames, we don't have to calculate frames. We just have to worry about what the wheels are doing for us. Okay? So it's supposed to shorten the amount of work that we go through and do. We really should be a little bit more explicit and note that unlimited frames. So again, I'll give you that second to hit the space bar and go through and solve this. So again, space. And ta-da, we find out that we can make 1 bike. Again, showing all that work. Okay? We might be at a point now where people at home are being like, this is dumb. I don't need to show this work. Why would you make me show this work? Okay? My question to that would be, did you score what you wanted to score on the previous exam? If you did, then no, you don't need to show all this work. If you did not score what you wanted to score, and you feel like your score was abysmally low, then you need to show your work. Okay? To add a little bit more insult to injury, I added 10 points to everybody's grade. You didn't score high enough. Show your work. Okay? Given 3 wheels and 2 frames, how many bikes can be gone through and made? This one adds a little bit more complexity. Again, go ahead and hit that space for me and solve it out. And we go through and check our work. Our wheels cancel. And in one case, and of course I jammed it all up on itself, in one case we would go through and see that we could make 2 bikes, and in the other case we would see we could make 1.5 bikes. So that means in whopping total I could make 3.5 bikes. You're right, that doesn't make any sense. You can't do that. The only amount of bikes I would be able to make would be 1, because then I run out of parts. Okay? That's what happens in this relatively small scale. Okay, so we just kind of stop at that 1 bike because I can't have half a bike, and I certainly don't have enough to make a whole nother other bike. Okay, so we have to run both conversions to see which one produced the smallest amount, and then we predicted based off of that. Okay, I'm also going to take a moment here to say I do sort of apologize for the saltiness. I'm really trying to help you guys push with these formulas, and everybody is stressed. So I do apologize for that. Let's try and refocus and get back into dealing with our conversions. Okay, so now we've got the basic format behind our conversions. Let's add one more layer of difficulty to this, because why not? Given 40 grams of wheels and 15 pounds of frames, how many bikes can be made? If we immediately start launching into our system, we want bikes. We're probably going to have to do this twice, but we'll just kind of write through this and see what we got. Bikes, and then let's just say we're starting with wheels. 1 bike, 2 wheels. How many wheels am I given? And now we run into a problem. I'm not given a number of wheels. I'm given a measurement of wheels. Therein lies the problem with our conversion factor, or our chemical equation. A chemical equation does not relate mass, it relates numbers of things. Okay, it's a counting unit, if you will. Okay, which means as soon as we introduce this mass, a measurement, we are going to need a new conversion factor. I can't just write in my wheels. I'm going to have to relate the number of wheels to a mass of wheels. Okay? That new conversion factor is not found in this question, and therein lies the problem. We can't solve this question. We could go through and write out what we would need to do. We need that conversion factor so that we could then do 40 grams of wheels, and so that everything would cancel out nicely. But since I don't have that conversion factor in the middle, I'm kind of stuck and I can't solve this one. Okay, so we encounter the same kind of thing in chemistry. Our chemical equation gives us the power to convert between substances, but it does not allow us to convert between measurements. Okay, so we have to be very, very careful when we go through and use chemical equations. Okay, so let's go through and shift to a chemical equation and see what, and of course all of that stuff shows up. So we're going to do some quick erasures. If we went through and looked at the chemical equation, this is very similar to the bicycle. A molecule is now a single unit. This is effectively bikes, wheels, I know that's sloppy, and frames. Okay, so it's a single unit being produced in each of those things, or a single type. Okay, the exact numbers are kind of different and arbitrary for that individual system. So the power of this chemical equation is that it can be infinitely scaled upwards. So if, for instance, you were going to make cookies, you could make the cookies from the recipe off the back of the bag. But if you needed to make a whole lot of cookies, you could just scale those numbers up, okay, depending on how many cookies you wanted to make. You could just add more flour. You don't just randomly add those extra pieces. You add those ingredients according to the ratio that the recipe told you. Okay, that ratio is established in your recipe. What we have in a chemical equation is a recipe telling us the number of these pieces. Okay, so why do I want to scale up? Well, do you only want 24 cookies? Maybe you actually want 24 cookies because you're making cookies for the rest of the people on lockdown. So you're going to make little gift bags and drop off bags full of cookies to each of your neighbors. That'd be really cool and nice. Okay, if you were doing that, maybe I'd give you my address, but that's a whole nother thing. Okay, so because you probably won't give me cookies, you'll probably give me eggs, which is not what I need right now. So in a chemical equation or a chemical reaction, what are we scaling up by? So I could, instead of doing 2 molecules, scale this up. Well, let's make it 1 molecule. Instead of doing 1 molecule of O2, I could do 1,000 molecules. Why? Well, as we discussed in the past video, 1 molecule is too small to weigh out. That mass is incredibly tiny. If I scale it up to 1,000 molecules, I can improve the odds of me actually measuring it. But if I scale it up 1,000-fold, I need to scale up the other ones 1,000-fold as well. Okay? But that now holds, and those ratios are now maintained. Well, that's still such a small value, it won't allow me to scale up, or I still can't weigh it. So what I'll do is scale it up even more, and instead of going up by just 1,000 molecules, I'm going to go up by 6.022 times 10 to the 23rd molecules. Okay? And that does seem a bit silly of a number, but it's fair. And so for the NO, which is twice the amount of O2, I could just do 2 times 6.02 times 10 to the 23rd, and I would end up with 12.04 times 10 to the 23rd molecules of NO. Okay? And I could do the same thing with the NO2 to figure out how many molecules of NO2. This kind of scale-up factor is similar to what we've already done. So let's backtrack here. I just said we multiplied that out, and all of a sudden it magically worked. Well, let's apply it a little bit differently. If I want to know how many molecules of NO2 I'm going to have, I would need to convert from the molecules of O2 that I'm given into molecules of NO2. So molecules of O2 would need to be in the denominator. NO2 would need to be in the numerator. That conversion factor is 2 to 1. Where do I find that conversion factor? That's coming from the coefficients from my balanced chemical equation. That's where the math that we saw on this other side is coming from. Okay? Why do we want that work? We want that work because if we start doing multiple conversions, it's very easy to lose track. By writing down the work, we can see what's happening there. So when we go through and run that math, we would then end again with our 12.04 times 10 to the 23rd molecules. Okay, and we might encounter the same question of, well, why the heck would we scale it up so much? Well, we scale it up so much so that we can weigh it. Why did we scale it up by this particular amount? Well, 6.022 times 10 to the 23rd is a mole. So I could write this as 1 times moles. The 12.04 was 2 times 6.02 times 10 to the 23rd. What did we just say 6.02 times 10 to the 23rd was? A mole. Okay. Same deal on the other side. That 12.04 was really 2 times 6.022 times 10 to the 23rd. What did we say that was? We said that was defined as a mole. Okay. And why does this help us out? We don't have to deal with the powers of 10 anymore. We can simplify this down to saying I'm reacting 1 mole of O2 with 2 moles of NO and 2 moles of NO2 and producing 2 moles of NO2. The measurement unit, if you will, the counting unit from our chemical equation can be molecules. It can also be moles. Okay? Which one's more useful is going to depend on the context of what we're doing. For most of what we do in general chemistry, it's going to be moles, not molecules, because moles we can measure. We can scoop out a bunch of stuff onto the scale, onto a balance, and get a measurement, a mass measurement for that mole amount. We can't get a mass measurement for the molecules, so the molecule conversion factor from our chemical equation is effectively useless because it is just too small. Okay? The same kind of thing can apply back to our bicycles. If we looked at a bicycle, you might be like, well, 1 bike and 1 frame and all of that fun piece. Why do I need to scale this up? Well, I can almost guarantee it that if you go to a bike manufacturer in China and you tell them the formula for 1 bike and 1 frame and 2 wheels, they're going to be like, that's dumb. I don't care about making 1 bike. I need to make 50,000 bikes because that's how I'm going to exist as a company. It's that order of scale. Most people don't have to deal with that order of scale because you're not the high upper end administrator within that company manufacturing those things. Okay? As a chemist, you are now that high end administrator. And not only are you that high end administrator, you're effectively God level administration because you're not looking at 50,000 particles. You're looking at 10 to the 23rd particles. Okay? Astronomically different in complexity and size. And so that's why we invent these new units to simplify our life. Okay? So with this, we can use that balanced chemical equation, and now we can answer questions of how do I convert moles of NO2, moles of N2 into moles of NO. Okay? Or how do I convert moles of O2 into moles of N2? Well, why would I do that? Well, if I have X moles of O2, how many of N2 do I need, okay, to run that reaction? So that single chemical equation, okay, so if we think back to what we've done before, we said, because this is the only one that I happen to remember, 454 grams was 1 pound. That expression, that equality, because that's effectively what we have here, is an equals, a chemical equation. The one expression that we did with our metric system, or even our English to metric, gave us 2 conversion factors. 454 grams is 1 pound, and 1 pound is 454 grams. So we get 2 expressions out of that for one memorization. Okay? So, and we could argue that we could just flip those back and forth, so it's relatively simple. A chemical equation becomes vastly more awesome in its potential, because if we look through those exact same types of relationships, what we end up with is now 9 relationships, or that's not 9, that would be 6 relationships, assuming there weren't duplicates, which I thought there were. We get a lot more relationships out of just this one chemical equation. Okay? If we think about the metric or measurement systems, those conversions, we got 2 conversion factors for one memorization. A single equation gets us 6 conversion factors. Okay? How many different equations, chemical equations, are known? A lot. Thousands upon thousands upon thousands, arguably an infinite number of chemical equations are possible. So every time we get a new chemical equation, we get a new conversion system, which is really, really cool. As long as we know how to pull that information out to establish those relationships, we have a lot of power at our fingertips. And that's what I want you to be able to pull from a chemical equation. That's the value and use to it.